Now we come to the important concepts. Probability and the state function. Probability concepts are very important in quantum chemistry. Let us start by defining probability. I will use the short PR for probability. Probability of an event is a number between 0 and 1. If probability is 1, we say that the event has 100% occurred. Otherwise, the lower limit means if a probability is 0, it simply means that the event did not occur. Now, it's a fundamental postulate of quantum chemistry or quantum mechanics is that when psi is given, all properties of the particle can be calculated using the given psi. This is a general postulate. If the state function psi for a certain energy level is given to us, all properties of the particle in that energy level can be obtained using the psi function. Now, one such property is the probability of finding the particle in a tiny volume element d tau. Now, this property, this probability is given by the following expression. The state function star times psi times d tau. This expression gives us the probability of finding the particle inside a very small volume, d tau. And of course, this volume is located around some point in space. This is the general form. It applies to any number of variables. But let us make it simpler and consider a particle with just one variable. Let us call that variable x. In that case, we will write and the volume element will be simply dx. So this expression here is a point x, here is a point x plus delta x. This is the interval is dx, delta x. This expression for x value indicated here on the graph gives the probability of finding the particle within this dx range. Notice that position of the dx depends on the numerical value of x. Say x could be that point or another point. X will change. And delta x is a non-zero finite number, but it must be small. And in fact, the symbol dx means a very small number. All right? Okay. Now, if the interval size is not very small, but larger size, say interval size, let us say large interval size, say from A to B. I'm assuming B is a larger number than A. Say if A is this point and B is that point, then you see B minus A is a large number. We cannot take it as dx. In that case, the expression for probability becomes, you take the same expression, but now you integrate from A to B for large interval sizes. And the result of the calculation, it is a definite number. I should write here, the psi that you use in such expressions must be normalized. Psi must be normalized. All right. Then the result of this calculation is going to give you a number between 0 and 1. That number is going to tell you the probability of finding the particle anywhere between A and B. All right? The total probability of finding the particle anywhere between A and B is given by this expression. You integrate this tiny probabilities from A to B. Please remember that integration is essentially summation, adding up. Therefore, for the large interval size, we are simply adding probabilities from each tiny interval. And because the function is continuous, summation becomes integration. All right. Especially because of the probability interpretation, not every function psi which come out from solution of Schrödinger equation is acceptable as for physical reasons. So there are general properties for the acceptable functions, and I'm going to list them to you. So requirements for physical acceptance of psi. One condition is that psi must be finite everywhere. Opposite of finite is infinite. All right? So this means that psi cannot become infinite at some point in space. And the reason for this comes from the probability interpretation. If psi becomes infinite at some x value, it would make the probability to be infinite. But this is physically possible or impossible? Probabilities must be between 0 and 1. So, therefore, psi cannot be, should not become infinite at any point in space, which means this, finite. Keep in mind, finite is the opposite of infinite. Second condition, psi must be a continuous function its variables. And the third requirement is that psi must be single valued. At all points in space. For example, the third requirement, that it must be single valued, is again related with the probability interpretation, because what does single valued means? There is a given x value, and if at this x position, if psi has more than one value, it will mean more than one value for probability. But probabilities must have just one value at the same point. Therefore, to make sure that this is the case, psi must be single valued. Now, there is an exercise, one in this lecture notes. Let us apply these ideas to the given function in this exercise. This I is the complex number. I is the square root of -1, complex number. K is a constant. And the question here is, show that K must be a real number. Real number for this function to be acceptable, physically acceptable. Please note that when we say some symbol is a constant, you should not think that the constant is a real number. You should start with assuming it is a general number, which means it could be a complex number. So K can be written as using two real numbers. Where A and B are real numbers. Any complex number is written like using two real numbers, remember? Now, then our function simplify a little bit. E to the minus I times A. Minus I times plus I. What is it? Come on now. I times I is minus 1, isn't it? Minus I times plus I is plus 1. So plus, there is x variable. B times x. This is exponential, so we can write it as e to the minus I a times x times e to the b times x. Right? Now, there are two factors here. And we are going to apply these conditions. The second and third conditions are obvious, that this function has a single value at every point, and it's a continuous function of its variable. So we just look at psi must be finite everywhere. It is this. I told you several times that finite is the opposite of infinite. Therefore, we make sure that by selecting, we are asking which numbers A and B are possible so that this function is not going to become infinite. All right? That's our guide. Now, there are two factors. We look at this factor, e to the minus I times A times x. This is, A is a real number, x is also a real number. This I makes the exponential complex. But this is, real part is cosine A times x, and the imaginary part is minus I times sine A times x. For now, we are thinking x ranging from, here, minus infinity to plus infinity, all right? For any real number A, for any x value in this range, cosine goes from minus 1 to plus 1. And what does it mean? Is it possible for this cosine function to become infinite at any x value for any a value? No. Same thing is true for sine function. Therefore, we conclude that this factor does not become infinite at any point for any value of a and x. Is that clear? Next, we look at the second factor. The second factor is this. Real exponential. B is a real number, x is also a real number. Now, let us consider the cases. B, positive values for B, and next, negative values for B. All right? Now, if B is a positive number, and You see x is going from minus infinity to plus infinity. If you consider positive x values, b is positive, x is also positive, and x, what is the range of positive values up to infinity? So x, when b is positive, x is positive, b times x is a positive number. As x becomes larger and larger and larger, what will happen? B times x will be a very large number. Therefore, when x goes to infinity, e to the infinity is present here, which will make the function value infinite. What does it say? Must be finite everywhere, including x equals infinity. Therefore, what do we conclude here? For this factor not to become infinite, b has to be just one value, 0. If b is 0, 0 times anything is 0. E to the 0 will be 1. Therefore, b has to be 0 from this argument. Of course, this argument must be also valid if b, for b negative values, but if b is negative, now b is negative, this time we think about negative x values, minus x values. Again, minus times minus will be plus. Therefore, in this case, when b is negative, as x goes to minus infinity, again, this function value will become infinite for all b values except 1. What is it? b equals 0. Therefore, we conclude that for this function to obey the first condition here, must be finite everywhere. It is necessary that b must be 0. But if b is 0, what is k? A. What is a? A real number. So, k values in this expression are necessarily real numbers because of that condition. All right. Our next topic is the concept of operators, which are essential in quantum chemistry. Operators. Now, let us define what is an operator. An operator is a mathematical operation that's applied to a function we use this symbol. You may call it hat or accent, but I will use the word hat. All right. And if we have a symbol A, for which represents something in our material, then when we use a symbol in its simplest appearance, without making it bold or italic, just the simplest way, such a notation, such a symbol, always means a scalar quantity, scalar. Scalar means just a single number. However, if you use a symbol, same symbol, but attach some mark on it, then it becomes, or we mean something different from a scale. Sometimes, for example, A, what do you understand? Vector. And this symbol is very different from that one. Here we have just one number, but a vector is more complicated. If this is a vector in 3 dimensions, you need 3 numbers to specify the vector. In our case, for the operator, we are going to use the hat on top of the symbol. So whenever you see a symbol with a hat, please remember that it is not a scalar, it's an operator. And an operator is something different from a scalar. When an operator is applied to a function, the result is in general, is a new function. In other words, the result of applying an operator to a function gives a scalar result, because functions are scalar quantities. So, e.g., example, let this symbol mean more explicitly the symbol I wrote on the right. This is the standard symbol for the first derivative, except that there is no function written here, but this is how operators look like. The meaning of operation is take the first derivative. Mathematical operation. Mathematical operation is take the first derivative. But in order to take the first derivative, you need a function. So here is what we write. The operator's function. Now we replace the explicit definition of this symbol. It is the first derivative. Okay, so operator D acting on F in this example, because D is the first derivative operator, simply means first derivative of F with respect to X. In general, derivative of a function is a different function than the original F. So keep that in mind, which means that when you apply an operator to a function, in general, you obtain a different function. But note also that the result is always a scalar, because whether it is derivative or not, and whether it is a function or not, it's a scalar. For functions, you are imagining that x values are under your control. X is the independent variable. So just imagine I put some x value there, x equals 2.5. Then what are you going to obtain? Just one number. It's a scalar. Now, quantum mechanical operators have linear property. It means this. if you have an operator A acting on the sum of two functions, if any linear operator means that you can expand it. This property for being linear is important because there are also some mathematical operators which are nonlinear and do not obey this property. For example, taking square root operation, simplest example. Take the square root, all right? Can you write square root of f1 plus f2 as equal to square root of f1 plus square root of f2? Is that possible? No. That's a nonlinear operation, taking square root. Here we are saying that all quantum mechanical operators are linear operators, and they all satisfy this relationship. When you have a sum, you can just expand it. And a related property is C is a constant, and operator A is operating on C times F. Operators never do anything. Our linear operators do not do anything to constants. All right? Constants are transparent to our quantum operators, and you may just factorize it. So these are the properties. There is, of course, an algebra of operators. Starting from some initial set of operators, we may construct more complicated operators from the given ones. For example, operator A1, two operators are given. We may write A1 plus A2, and this will become a new operator. Let us call it operator A3. Or we can write this symbol. It looks like A1 times A2, but don't forget, these are not scalars. But it is just for notational purpose we are writing it, A1 times A2. And this gives us a new operator, say A4. Now, what are the definitions of these? You take the operator and apply it to a function. Please note our notation. Functions should always appear to the right side of the operator. Don't write it like this. Doesn't make any sense. All right? By definition, operators are not operating to the left. They are operating to the right. So you put the function to the right. Here also. What is the definition of A1 plus A3? It is A1 plus A2. Now you expand this. All right. The operation of A3 on any function f is this expression using A1 and A2. Similarly, for this operator, now you write explicitly now you expand this. How do you, just like we have expanded this expression into this form, the operator which is nearest to f First, you will do that operation. So you will do this. Parentheses means you apply A2 to F and then simplify as much as you can. And so this is the final result after applying A2 to F. Then you take this final result and apply A1. This is how the compound operators of this type, A1 times A2, are defined. I will give you an example. Efendim? Burada. Bir altta değişir. Toplamalarda değişir. İşte burada değişemez. Yok. Çünkü we are going to discuss that. Changing their order is described by the word commutation. Commutation. Commutation means if there are two things next to each other, just change their places. All right? And we are going to discuss that. If you change the places of A1 and A2, put A2 here, A1 there, in that case you will obtain this. If in general, the result of this type of operation, the final result, is not the same as this one. We say that in general, the two operators do not commute. There are cases where you obtain the same result. Then we say the two operators commute. So we have just two possibilities, either commute or do not commute. We will come to that, but after the example. Here, one operator is X times D, and the second operator is the reverse, D times X. All right, now here X, this symbol, X is the variable symbol, all right? Just writing it as X without any extra mark means that it's a scalar. X is just a number you select, independent variable. Now, the X operator X, its definition is this. The operator acting on F is numerical value of X multiplied by F at the same point. This is the definition of the X operator. We say that X operator is a multiplication operator. Multiplication operator. Multiplication by X. Here, if you call this A1, this is A2. This one is the reverse, A2, A1. All right? Now, let us see if they produce same result or not. What we do is we start with one of them, say the first one, and then apply it to any arbitrary function. You do not put some known function, explicit function, but you assume any function can be put here. Next, you simplify this expression as much as you can. So I'm applying this. Now I will simplify the parentheses. What is the definition of the first derivative operator, isn't it? So this is just, this is all I can do, because explicit f is not given to me, so I stop here. For the parentheses, I stop here. Next, I simplify this one. What was the definition of x operator? Multiply with the scalar x. So I write this. This is my final result for the simplification. Next, I repeat the procedure with the other one. Now simplify the parentheses. What does x operator times f? Definition is multiply with scalar x. It is this. Notice, the result is a scalar. Now apply the definition of d. What was definition of d? Take the first derivative. Now, can we further simplify this expression, even if we do not know f explicitly? Yes, because this is a product here. Derivative is derivative of the first factor times the second factor plus first factor times derivative of the second factor. So, derivative of x with respect to x is 1 times the second factor f plus x times derivative of f with respect to x. Now we compare these two results. This result with this one. Are they the same? No. Therefore, the order of the operators, whether you write it this way or the other way, does it matter or not? It matters. So the general conclusion is here, operators in general do not commute. What is the difference between them? So we are writing this. XDF operator is, the simplified form is this one here. X times minus dx acting on f. The simplified form is this expression. F plus x. And can we simplify this expression here? What you see here? You see x times first derivative is with a plus sign here, because this is a minus sign. There is also x times first derivative, so they can cancel. What is the final result? Minus f. Yes. So this is like A1, A2. This is, the orders are, they are in different order, A2, A1, acting on the same function. and the result is non-zero. All right? We say that the operators x and d do not commute. In fact, we write it, let us write it this way. Write this as minus number 1. So 1 is an operator. Number 1 is an operator. Its definition is multiply the function with 1. Why am I doing this? Because I want to collect operator on the left side in a suitable way, and I need an operator on the right side because types of quantities must be same. You cannot have operators on the left side and a scalar on the right side. If there is an operator on the left side, there should also be an operator on the other side. So here I will write it, formally factorize this. Now formally write it minus number 1 operator. You see, this part is an operator. This is an operator. Operator on F equals operator on F. Now I can conclude as an operator equality all right. Now this word. If the final result for this subtraction were 0, we would say, we would conclude that there is no difference whether you write the operators as x then d or first d then x, if the result were 0. However, this procedure showed us that the difference is not 0. We say that operators x times operators x and d do not commute. There are just two possibilities when you consider two operators, two different operators. Either they are going to commute or they are not going to commute. No other chance. In general, two operators do not commute. But there are some exceptions, let us say, exceptions in which the two operators do commute, which means the order doesn't matter. And it turns out that that case is extremely useful. Our time is up, but this part is called commutator. In general, commutator is this one. You take two operators. First you write A1 times A2 minus, reverse the order, A2 minus A1. This expression is called commutator of A1 and A2. All right.